just go, oh, well, it's just this, it's just a fact. Or where you have to apply something, or calculate something, or analyze something, and you all know what those questions are like, having gone through all the courses you have before and what we've already done. Now, obviously, like those contrast and compare, that's a higher level question than something else. I'll show you an example coming up. Each of the items and rationale are worth a maximum of 10 points, so you can get 50 points out of this. This is low-hanging fruit. You can get a lot of points out of this. You know, quite frankly, you do a good job, and because what I want you to do is, and you'll do yourself a big favor, if there were a couple of areas in Unit 1 that weren't clear to you, get in, review that material until you're pretty comfortable with it. If you have a question, ask me. And, you know, maybe I can make that material more clear to you, and then write a test item. When you write test items, you really figure out for yourself if you understand it or not. And so it'd be great if you wrote items and rationales on things that were previously unclear to you, because that is automatically going to help prepare you for the final. Now, this isn't mandatory, but whenever possible, cross-link information from one unit to another unit. It's not mandatory. It can be a pure Unit 1 question, pure Unit 2 question, whatever. I'm going to show you an example of an item where I linked forward, and there were several items in Unit 1. Remember, Unit 1, much of that was foundational physiologic processes. And we've been talking about diffusion and gradients and things like that, really for the balance of the semester. The rationale, and I'll show you what I want you to do with the rationale: provide the correct response. You'll explain why that's the correct response, and as importantly, you'll explain why the incorrect choices are incorrect. And this last line is really important. I want you to write your rationale as an explanation to your future self. You're writing this for yourself. So if you are to read this 1 week and 6 days from now, okay, you can read that, and you've written it to yourself, so you'll be cued in on what are the facts, what are the concepts associated with this item to help you remember what you should remember. So the best thing you can do when you're writing explanations of things, write them to yourself in the future. So here's an example of, this was a Unit 1 item. In pulmonary physiology section to come, you will study how oxygen flows. I was very careful what word I used there, from tissue capillaries to tissue cells by simple diffusion. The driving force for simple diffusion is provided by A, surface area available for diffusion, thickness of the diffusion barrier, difference between capillary and cellular oxygen. Okay, there's some things I worded differently than what we've talked about before. So, correct response is C, the difference between capillary and cellular oxygen is the driving force. And so choice A is an incorrect, because although surface area impacts diffusion rate, i.e. as surface area increases, diffusion increases in a direct relationship. Surface area is not a driving force. It's a determinant, but it doesn't drive it. Choice B is similarly incorrect. The thickness of the diffusion barrier impacts diffusion rate, such that the thickness of the diffusion barrier, as it increases, diffusion rate decreases. It's an inverse relationship. Choice C refers to a difference. And any time you have a difference across compartments, you're talking about a gradient. Here we're talking about the partial pressure gradient of oxygen is what provides the driving force for oxygen diffusion. As oxygen diffuses down its gradient from an area of high partial pressure to an area of low partial pressure, that's That's what happens. Moreover, as the gradient increases, diffusion increases, so it's a direct relationship. So you know, just explain why is the correct correct, why is the incorrect incorrect. Do it on something that you think you're learning new information. Obviously, I can't tell if that's what you're doing, but it'll do you the most good, okay? Now, the idea was to post these for everybody to use them, and some of them I might post anonymously, some I won't. If I elect to do it, or if I elect not to post one of your questions, don't think you did badly on it, because sometimes it's like, okay, I'm happy that that person is understanding it this way, but I know because of questions I get from other students, that would lead to a problem. So sometimes when I've done this in the past, I don't post people's items and rationale, because I know how 60% of the class views something, and this doesn't mean your explanation's bad sometimes. Sometimes they are. I've had that happen. But, so this is all posted to Moodle, so good luck with it. Have fun with it, because you can. But more importantly, learn something from it, okay? So we finished off last time looking at how the nephron, how the kidney handles water. And water is one of those very important things that it's freely filtered, but we don't want to lose it all in all of the from the body as urine. We want to put it back into circulation. So we already went through this, that because of the architecture of these nephrons, you have a lot of water reabsorption in the proximal tubule. You have water reabsorption, and the descending limb of Leukopenly, there's no water reabsorption. In the ascending limb, because it's impermeable, by the time you get over here to the beginning of the distal tubule, just because of the architecture and the concentration gradients around that nephron, you've reabsorbed 80% of your water. It's only over here, primarily in the collecting duct, that you can physiologically regulate, fine-tune, so to speak, how much water you reabsorb, and therefore how much is going to be lost in the urine. So you have potential for water reabsorption all along that collecting duct. And one of the biggest determinants of how much water is going to be reabsorbed is antidiuretic hormone. Its name tells you what it does. Antidiuretic. Diuretic means water passing through. And so it inhibits water passing through and into the urine. Diuresis, a diuresis is urine passing out of the body. So antidiuretic hormone inhibits diuresis, okay? So the more ADH, and the other name for it is what? Vasopressin. The more water is reabsorbed from the nephron back into peritubular capillaries. Now it's in the bloodstream. If you don't have any ADH in the system, that is a condition called diabetes insipidus. Has nothing to do with sugar diabetes, as great-grandma might have said. But there'll just be a huge amount of urine output every minute because there's no ADH stimulating the reabsorption. If you're under maximum ADH stimulation, for example, you're extremely hypovolemic because you're thirsty, you're dehydrated, your body wants to save what water is in circulation, you don't want to release it as urine, you'll produce very little. This is how much is produced every minute. Okay, so we're going to see that water follows sodium in most places in the kidney. And in this basolateral membrane, you have aquaporins that will allow water to diffuse out. But in that collecting duct, you have vasopressin or antidiuretic hormone receptors, same thing, that when it binds the receptor, it turns on a cyclic AMP process, which causes this aquaporin type 2 that these cells are making, but these are just like players sitting on the bench. They're sitting in your Golgi apparatus. And what happens is this activation of the cyclic AMP pathway, it causes this vesicle with this aquaporin to come to the surface, so you'll have more of those aquaporins, and therefore you'll have more water reabsorption. So in the presence of ADH, you have more of those channels, more water can be reabsorbed. And I'll show you later on that there's a reason for it. The osmolarity here is lower than the osmolarity is over here. So there's an osmotic draw. Once you have channels and those channels are in place, there is a drawing force to draw that water from the lumen of the nephron out here into the space, the interstitial space, before you get to the peritubular capillaries. So that's the big picture. Yeah, no, not quite yet. Most places, as I mentioned, water follows sodium. We're going to see there's many different sodium reabsorption mechanisms. When sodium is reabsorbed, that lowers the osmolarity here, and what that would do is that increases the water concentration, so water is going to have a tendency to follow in the same direction as sodium. It's not clinging on to sodium, but as more and more sodium comes across, that increases the osmolarity over here, so water is drawn from an area of high water concentration to a relatively lower water concentration area. And then here in the peritubular capillaries, you have a lot of osmotic pressure because the plasma proteins are packed in there. So they will just, and these are quite fenestrated. They have gaps in them, and they will just draw sodium into those capillaries, and then that draws water into the capillaries. So you get reabsorption and back into the circulation. Okay, so let's now look at sodium. Same type of thing. Here's this strange way to lay out a nephron, but at least you can see in 2 dimensions what's going on. So sodium is freely filterable. It's freely filterable. It comes across at the glomerulus, no problem. So let's look at the amount of sodium that is filtered in a minute. Let's say, so here's 100%. This is all the sodium that's been undergone glomerular filtration. We're going to say that's 100% of the sodium that's come across. Just going across the proximal tubule, 2/3 of sodium is reabsorbed. We're going to see that that's the case because sodium is going to be helping for the co-transport and counter-transport of a lot of molecules. So a lot of molecules depend on that sodium to help drive transport processes. So as a consequence of sodium helping out all these transport processes, 2/3 of it gets reabsorbed just in the proximal tubule. Now going down the descending limb of the loop of Henle, there really isn't any drive for sodium reabsorption. Going up the ascending limb, there is an active process. It's chloride-driven sodium reabsorption, and it's a pretty involved transporter. It's more than just sodium and chlorides being moved, but it's actively pumping chloride out from the lumen of the nephron here into the interstitial space. And guess what? Sodium then follows. It's pumping out this negatively charged chloride, so sodium electrically follows it. So that causes some additional sodium reabsorption, such that by the time you get to the beginning of the distal tubule, you're down to 9% of that original filtered load of sodium. You've reabsorbed 91% of sodium. And that's just due to the architecture of the nephron. A lot of sodium, and sodium, you need it. You know you need sodium because it drives so many transport processes. It drives so many membrane potentials. You don't want too much sodium, you don't want too little, you want it just right. Well, this is one way your body keeps it just right. Just like water, the final water reabsorption in the nephron, it's here in the distal tubule where you fine-tune how much sodium is going to be reabsorbed and put back in the bloodstream and how much is going to be released in the urine. And that is largely under the control of aldosterone. Aldosterone is a steroid hormone. It's produced in the adrenal cortex. And you've already seen what causes its release. Angiotensin II. Angiotensin II is a releaser of aldosterone. It's one of the releasers. You'll see that there's some others. Now, if you don't have any aldosterone in circulation at all, about 2% of the original filtered load of sodium is going to be lost in the urine. And that's actually quite a bit. You can lose a lot of sodium very quickly with that amount. Now, if you happen to be hyponatremic means low plasma sodium. A normal healthy person, you'll have a lot of aldosterone in circulation, and you'll have essentially no sodium at all being released in the urine. Nearly 100% of it is going to undergo tubular reabsorption and go back into the bloodstream. Okay? So, there's a lot of different ways that sodium is reabsorbed. Here is the unidirectional transport of sodium, and this occurs in the very late distal tubule and in the collecting duct. This is stimulated by aldosterone. I'm going to show you a slide coming up, but aldosterone, so ADH is a peptide hormone. Aldosterone is a steroid hormone. As a general rule, which one works more rapidly? Peptide hormones or steroid hormones? Peptides do. Because peptide hormones, what they basically do is they just kind of like flip a switch. There's already the machinery here, the wires, the electricity, the bulbs, and peptide hormones just flick the switch to turn on or turn off existing machinery. Steroid hormones, going back to part one, what do? They change gene expression. So what does aldosterone do? Aldosterone builds light bulbs. It puts in new wiring. It actually builds new power plants. That takes a little bit more time. Than a peptide hormone. But steroid hormone effects tend to be long lasting, whereas peptide hormone effects tend to be shorter lasting. So, this process, is stimulated by aldosterone, and what happens is sodium's going to enter this tubular cell, going down its concentration gradient. Why is there a concentration gradient? Because we have that sodium-potassium ATPase exchange pump that we talked about in part one. And then because of a high osmotic pressure inside the peritubular capillary, sodium is swept in by what's called bulk flow. Movement into the peritubular capillary is not by diffusion, it's by bulk flow. It's like vacuuming things in. Now, because sodium is moving from left to right, water follows. Water follows here in the collecting duct. So not only in the collecting duct does aldosterone cause sodium uptake, it also causes water reabsorption as well. Yeah?
So if you're hyponatremic, then you're not going to absorb as much water, right?
So you are hyponatremic. So your body's going to try to save what sodium it has. It's also going to try to save what water you have. So you're going to, your urinary volume is going to go down. Which sometimes isn't what you actually want, but we can talk about that later. Now, what also happens when you're under strong aldosterone control, you also get tubular secretion of potassium. So potassium starts to be lost in the urine. Now, why is that? Why we have this sodium-potassium ATPase exchange pump. So aldosterone will stimulate tubular sodium and water reabsorption, and it stimulates tubular potassium excretion. So this is, I should have put this earlier in the slide. This is really how water is handled, but sodium is going to go down its concentration gradient. It's going to come in, and when sodium comes in, water is going to follow by osmosis. Has to go through aquaporins, and then bulk flow sweeps both sodium and water up into these peritubular capillaries. The plasma proteins are packed in there, so there's a lot of drawing, pulling potential in those areas. So, I've mentioned at least twice, so goes sodium, so goes the kidney. Many different useful molecules. Your body wants to reabsorb them. And so there is tubular reabsorption. For example, the example I have on here is glucose. Your body does not want you to release glucose in the urine. It's a useful molecule. You want to return it back to the bloodstream. How do you get it back into the bloodstream? By co-transport processes. We talked about secondary active transport in Unit 1, and here's an example of it. So sodium, all the monosaccharides, so fructose, galactose, all the amino acids, water-soluble vitamins, lactate, et cetera, they are largely reabsorbed. The good guys, they are reabsorbed, and many of them are reabsorbed almost exclusively in the proximal tubule. Why? You have specific sodium co-transport proteins in the proximal tubule. So all these co-transport processes utilize a carrier transport protein on the luminal, or called the apical membrane. And these carriers, remember, they're very specific. A glucose transport protein will not carry the amino acid alanine. So think back to part 1, all those rules still apply. All these carrier-mediated transport processes, because they are utilizing a transport protein, they all have Tmax, transportation maximum kinetics. They can all be saturated, things we talked about in part 1. So sodium and its co-transport substance, what do? They loosely bind. So let's say glucose loosely binds to this co-transporter, and there's a concentration gradient against glucose, so glucose can't come in by itself. But sodium, remember, you have a 10-fold concentration gradient. Sodium comes here, binds, and it's sodium causing a conformational shift in that protein that brings both sodium and glucose into that cell. So that is an example of secondary active transport. It's secondary because ATP is not being used in step 1. And more specifically, it's secondary active co-transport. 2 molecules are going in the same direction. One has to be going down its chemical concentration gradient to drive this, and in this case it's sodium. In almost all cases it's sodium. How do you keep sodium low in here? That sodium-potassium ATPase exchange pump. And then glucose can leave by facilitated diffusion. We have a high concentration here, low concentration there. We have facilitated diffusion going on right there. Now, we have, once again, co-transporters for all the different amino acids. We have co-transporters for alanine. We have co-transporters for water-soluble vitamins. We have a co-transporter for galactose. All of them are driven by sodium going down its concentration gradient. So sodium going down its concentration gradient provides the driving force for all of these co-transport processes. So sodium glucose co-transport, sodium's driving glucose across. Sodium alanine co-transport, it's sodium going down its chemical concentration gradient, driving across. So much of this occurs in the proximal tubule. That's where you have these co-transporters. There are a couple of other co-transporters that are also found, for example, in the distal tubule. But most of these, they're found, by and large, almost 100% in the proximal tubule. So guess what? Not only are you reabsorbing glucose, you're also reabsorbing sodium in the proximal tubule. Remember, just from the start of the Bowman's capsule to the end of the proximal tubule, you reabsorb 2/3 of your filtered glucose. That's because it's doing so many jobs for you. So look back on Unit 1 and go, okay, as concentration gradient goes up, you can transport more and more. So there, do remind yourself, the only reason why I put this in here, I want you to remind yourself about Tmax and saturation kinetics. And in all these co-transport processes, you have X number of transporters and each of them can only work so fast. So therefore, there's a maximum transportation rate. And when all of those carriers are busy at the same time, they're said to be saturated. That's the only reason I threw that in here. So here's just a quick little way of looking at this, and that program learning packet that I told you to wait till after today to go through, where you do all the top panels first and then you do the bottom panels, that will talk about glucose handling. So let's look at, typically for monosaccharides, amino acids, water-soluble vitamins, typically 100% of them are reabsorbed in the proximal tubule in a normal, healthy person. And all of those are chained to sodium reabsorption, sodium co-transport. You have some of this in that handout. But you know that a normal plasma glucose is 100 milligrams of glucose in every 100 milliliters of blood. So your kidney is set up. It'll easily do that. It'll get that sodium reabsorbed, 100% of it, no problem. But what if your fasting glucose is a little bit higher? No problem, you've got a physiologic reserve. It might take a little bit farther down that proximal tubule, but you're going to get it 100% absorbed, no more glucose in there. What if it's even higher? What if it's around 250? Well, you do have the capacity, more glucose over here, more going to be filtered every minute. Glucose is freely filterable. You have a capacity to reabsorb 250, a little bit more, up to about 270, 280 milligrams of glucose in every 100 mils of plasma. You can get it all reabsorbed. But what if you have a very poorly controlled diabetic and his or her plasma glucose is 400? What happens is, yeah, you can reabsorb your 250, but the remaining glucose is going to go down the nephron. And once it enters anything beyond the proximal tubule, that glucose is doomed to urinary excretion. Why? There are no more sodium glucose transporters any place in the rest of that nephron. So if you have glucose here, you sure as heck are going to have it here, coming out as urine. And glucose has a lot of OH groups. OH groups attract what to it? Water. So, if glucose is coming out in the urine, what's it going to drag with it? A lot of water. So an uncontrolled diabetic with sugar or glucose in their urine, they're going to be undergoing what's called an osmotic diuresis, because the osmotic effects of glucose, they're going to have an increase in, yeah, I know you all have had, whoops, probably can't see that, but diuresis is a perfectly descriptive name. Whoops, go back. It's not going in the direction I want. Very strange. So esis means condition of, means urine, and dia means through. So it's a condition of urine flowing through. And osmotic diuresis is simply an osmolarity situation that is causing that increase in urinary output. Okay? So that program learning packet is going to help you understand the handling of glucose in the kidney. Now there's a couple of other co-transport processes here. This is actually that chloride-driven sodium reabsorption, and it's more involved in this. There's more ions involved here. But this is a co-transport process. It is a primary active co-transport process. And this is in the ascending limb of the loop of Henle, and there's active reabsorption of chloride causing sodium to follow that negatively charged chloride. So as you might expect, there's more things going on because what do you do with chloride? But this is another way. This is another way that sodium is reabsorbed. This takes place in the ascending limb of the loop of Henle, that ALH, that's ascending limb of the loop of Henle. And this is the one place where you don't see water following sodium. It's because that ascending limb is impermeable to water. Okay, there are co-transport processes that are very much dependent on sodium movement. And in the proximal tubule and in the distal tubule, here's a very important one. A sodium hydrogen ion counter-transport process. This is very important for pH control. And it does some other things for us too. But sometimes you need to pump a proton out. Well, sodium coming into the cell, going down its chemical concentration gradient, will allow, using this co-transport protein, the other term for co-transport, this is a counter-transport protein. Another name for a counter-transport protein is an antiport. So counter means two things moving, but they're in opposite direction. Co means two things moving, but in the same direction. So this is a sodium hydrogen ion counter-transport protein and process. So this is very important for pH control. You find this counter-transport protein in the proximal tubule and in also the distal tubule. And believe it or not, pumping out this proton is going to be very important for bicarbonate reabsorption. It's also a way of getting the acid out of the body. So this is what figure 1414 shows you. A lot of different things. There's sodium co-transport, there's sodium counter-transport, there's sodium diffusion. So this is going on in a lot of places throughout. This right here is what you would see stimulated by aldosterone in the collecting duct cells. So do look at 1414 and more importantly, read the caption associated with it. Okay, how about processing? everything that's inside the nephron is either luminal fluid or nephron fluid, but it's only when you have that fluid leaving the collecting duct, then it's urine. And all of you have heard about this counter current multiplier system and so forth. And boy, for the longest time when I was a student, I didn't understand how this worked. I could answer a lot of questions, but it didn't make sense. Well, I was missing two key things, which I'm going to point out to you. And hopefully, if this was ever... How many of you had a lot of renal in your undergraduate? Quite a few. How many of you found some of it confusing? You know, and I'm going to show you what I found confusing. Now, this part makes sense to me. Now, here we're looking at osmolarity, and we're rounding everything up. Your plasma osmolarity is really about 285, but we're rounding up to 300, just for a nice round number. So let's say your plasma osmolarity is 300 milliosmolar. Well, glomerular filtration is what's called isoosmotic. The osmolarity, I should say, of that original filtrate is the very same as what was here in the plasma. Why? Water's coming in, ions are coming in. They're freely filterable. So if it's 300 in the plasma of the glomerular capillaries, it's 300 in the beginning of the nephron. Now you already know that about 2/3 of the water and many of the solutes, not all the solutes, they're reabsorbed. And as you go across the proximal tubule, the osmolarity of the fluid in the proximal tubule is said to be isoosmotic. It stays 300. So yep, you have water and you have solutes being reabsorbed, but the concentration of the fluid really isn't changing. Now, I should have done this one step at a time, but if it's 300 here, and if solutes are staying in place, if solutes are staying in the descending limb of the loop of Henle, but water is coming out, what's going to happen? Is that luminal fluid going to become more concentrated or more dilute? More concentrated, and that's what this is showing. As water is coming out, but the solutes stay in place, that luminal fluid gets more and more concentrated. Till we get down to the bottom loop of Henle, and this can be 1200 in some people, this can be 1400 in other people. It's kind of genetically based. If you happen to, your ancestors lived in arid environments where they needed to really conserve water, this might be closer to 1400. If you, your ancestors were people who lived in areas where fresh water was plentiful all the time, no, the selection was probably different. Maybe it isn't so high right here. It might be 1200. So this is 1200 to 1400. You'll see two different textbooks say different things. So what I want you to understand is the luminal fluid becomes more and more concentrated as you go down that descending limb. Now, coming over here to the ascending limb, you already know that we're pumping out sodium chloride, and this segment is, how does it handle water? It's impermeable. So water's going to stay in place, but solute is coming out. So do you think it's going to become more concentrated or more dilute as that fluid goes up the ascending limb?
Dilute.
Pardon me?
Dilute.
I agree. It's going to become more dilute. Solutes are coming out, water's staying in place, and that's exactly what happens. It becomes progressively more and more dilute. Okay, so I want you to notice, in the proximal tubule, that osmolarity is equal to what's in plasma. So it's, what do you find inside the proximal tubule? You find isoosmotic solution. What do you find in the descending limb of the loop of Henle? You find hyperosmotic solution. What do you find in the ascending limb? Well, you find hyperosmotic. So everything's based on that 300. So that's higher, that's equal. So that's isoosmotic. But by the time we get up here to the beginning of the distal tubule, it's all the way down to 100. That's hypoosmotic solution, because you compare everything to plasma. So in the descending limb, you have hyperosmotic, isoosmotic, and hypoosmotic. This is built into the nephron. Now, I'll tell you what, when I had physiology for the first time, my brain rebelled, because it's like, why on earth are we built to concentrate it just to turn right around and dilute it? It seemed like a big waste of time to me. I could answer a lot of questions, but I didn't understand what this whole process was doing for us. So, big important point is by the time we get to the beginning of the distal tubule, we have a dilute luminal fluid. It's dilute. It's about 3 times more dilute than what plasma is. Okay, this is going to give us an option. I didn't realize it at the time. And there's something else very important here. And we're going to get to that in a second. So you hear about counter current. Well, here fluid is going in one direction, here fluid is going in another direction. That's one of the counter currents. There's another counter current, which I'll show you. So that's where that counter current name came from. So why is water being reabsorbed in the descending limb of the loop of Henle? Well, it's because of this. Our efferent arterioles come out, and here's the peritubular capillaries. They now have, because of so much water coming out here, these proteins are now packed. And because they're packed, they will draw this sodium and chloride into the peritubular capillary. So now we have packed proteins, we have sodium chloride. Yep, we don't have any water reabsorption over here because it's equilibrium. But by the time it gets over here, we have a lot of sodium chloride, we have packed proteins, so there is a draw. You can draw water out of that descending limb of the loop of Henle, and it's going to go in that peritubular capillary. So that peritubular capillary is drawing water toward it in this area. Guess what? This is going in the opposite direction of this. So this is a second counter current. This blood flow is going this direction. The luminal fluid's going that direction. So we have 2 counter currents going on. And I kind of thought, well, that's a big whoop. I don't care. Well, here's the big point. And yeah, these peritubular capillaries are wrapped all around all this. I did not realize the consequence of having this loop and this counter current system. And one of the big consequences is this. Because of the movement of these ions, you develop an osmotic gradient out here in the interstitium, outside of the nephron. And it is very much regulated by what's in the descending limb of the loop of Henle. This is just a PowerPoint problem here. This is supposed to all be the same level. So if it's 300 here, the interstitium equilibrates to whatever it is in the descending limb of the loop of Henle. So it's 500 here, it's 500 at this same level, all the way across. If it's 700 here, it's 700 at this level, all the way across, 900, 1200. And remember, there's a nephron in front of this, there's a nephron to the right, nephron to the left, there's a nephron in back. So this is 3-dimensional. So this counter current system has done 2 things for us which I did not appreciate. It's made dilute luminal fluid here, and it's created an osmotic gradient. As you go down farther and farther, it becomes more and more concentrated. This gives us options. This gradient, something with this, with an osmolarity of 1200, would that have a high water concentration or a low water concentration?
Low.
A very low water concentration. The higher the solute, the water, lower the water, right? So what that means is if you open up a water channel here, it's going to pull water toward it. Aha. So that interstitial osmotic gradient that gets more and more concentrated as you go farther and farther down is a potential drawing force to draw water out of the nephron if the body opens up water channels. Oh, I didn't get that when I first took the course. So let's kind of put it all together. We have reabsorbed a lot of water, we've reabsorbed a lot of sodium to get to this area right here in the nephron at the beginning of this tubule. We now have a dilute solution. It's not nearly as concentrated as what plasma is. So we now have an option. If we don't open up any water channels at all, let's say we have more water in the body than what we need, and we need to get rid of some water. So there won't be much antidiuretic hormone in the system. These water channels here won't open. Guess what? We release a dilute urine. That's a high water concentrated urine. We can release a high volume. If we don't open up water channels, we have the option of releasing a very high volume of a very dilute urine, and that would help us. But what if we are very much dehydrated? And if we're very much dehydrated, ADH will be in high concentration in solution. ADH will be opening up water channels all along this collecting duct. So as this dilute solution comes here, this is a much higher water concentration than what you have out here. Water's going to flow out until it gets all the way to 300. Then that solution will come to here. It encounters another water channel. Well, 300 is more dilute than 500, so more water is going to be reabsorbed. As we go farther and farther down the collecting duct, as long as the water channels are open, you're going to be reabsorbing more and more water. So, we can release a urine as concentrated as 1200. That is a low volume, highly concentrated urine. The architecture of this nephron does a number of things for us. Number one, it's built in a lot of water reabsorption, even by the time you get here, before you finally regulate how much water is reabsorbed. You have a lot of built-in sodium reabsorption. But because of this interstitial osmotic gradient and because of this dilute solution right here, we have the option of releasing this directly as a very dilute urine. We can concentrate it all the way to here, have a very concentrated urine, or anything in between. We have an option of releasing a urine that's someplace between 150 to 1200 milliosmoles. That's what this loop gives us. We can release dilute urine to get rid of water when we have too much of it. If we don't have enough water in the body, we can return almost all the water because of the drawing potential of that interstitial osmotic gradient. How you doing? So we have an option going here, here, and anything in between. That's not a bad thing. You can get rid of excess water. You can keep the water you need. Or as you're sitting here, drink a little, lose a little. Everything's okay. Yes?
So you said though that's the osmolarity of the interstitium compared to the capillaries?
Yeah, so this is in the interstitium.
Okay.
And in the peritubular capillaries, you have you have actually high, when you look at how it comes across, goes around a nephron, you're going to have high sodium chloride by the time it's here, and you're also going to have packed proteins until the water is reabsorbed in the peritubular capillary there, and that will dilute out the protein to what it was normally. That's bulk flow. So this is the range that you can release for urine, as dilute as 150 milliosmolar to as high as 1200. So this right here, if it's 150, that'd be a high volume of a very dilute urine. This would be a very low volume of a very concentrated urine, and anything in between. It's a masterful piece of architecture here. It took me years to understand, but it's because I didn't get that we make this and we make that, these two green encircled things, and that gives us options for the body to fine-tune sodium and water reabsorption. Not a half-patted bad piece of work. So, regulation of sodium balance, already talked, aldosterone regulates here in the collecting duct in the very, very late part of the distal tubule. So aldosterone's actions, it causes sodium reabsorption. Water is going to be reabsorbed because it follows sodium in that area. There is going to therefore be less sodium in the urine, and there's going to be less water, so urinary volume goes down. That's going to cause, aldosterone causes water reabsorption, that's going to, over time, it can increase your extracellular fluid volume. So if it started out to be too low, this helps to restore it. And there is potassium tubular secretion with the effects of aldosterone. This gets to what does aldosterone do as a steroid hormone. Aldosterone, it's a steroid hormone, it's from the adrenal cortex, and so therefore it binds receptors found, intracellular receptors that will affect gene expression. And what does it do? It causes the synthesis of these chloride channel proteins that you need in the lumen, the luminal membrane. It stimulates the synthesis of this sodium potassium ATPase exchange pump protein. It also causes the biogenesis of more mitochondria. What do mitochondria do? They produce ATP to power the pump to allow more sodium to come in. Man, is that comprehensive or what? Aldosterone builds new machinery to really be able to increase more sodium reabsorption. So that takes an hour or two to really get going. So you build the power plant, you build this ATPase exchange pump, you build the channel proteins, you increase synthesis through increased transcription and translation. And therefore you have a much higher capacity for tubular reabsorption of sodium. It takes about 20 minutes for this to get started. It takes about 2 hours for that to be working at a pretty high rate, but even over a day it'll still keep getting higher and higher. Now, we've already talked about the angio. Oh, I'm sorry, Kim.
On the previous slide, so then if it takes 2 hours for it to get going and everything, how long does it take for it to then degrade?
Oh, it's not as, it does have long-lasting effects. It has steroid effects tend to be long-lasting, but it's one of those things, if you don't use it, you'll lose it. So if the drive, and it does take continuing aldosterone to keep these things upregulated. So if people are in a high aldosterone situation, it will take 1 to 2 weeks to get back to the very beginning stage. If they were in very, very high aldosterone condition. Most of us, we just increase or decrease it a little bit throughout the day, so within a day, we're back to normal. But if you have been in a very high aldosterone situation, it takes a long time for it to completely come down. But that's not the case of what we're going through hour to hour and day to day. It's not nearly as dramatic. Okay, so we already saw that one way of releasing aldosterone is by this renin-angiotensin aldosterone system. This is really kind of used in emergencies to release a lot of angiotensinogen and release a lot of aldosterone. Minute to minute, hour to hour. What stimulates the release of aldosterone? Well, it's plasma potassium. If you have elevated potassium in the bloodstream, what this is saying, elevated potassium will stimulate, that's what the plus sign, stimulate the adrenal cortex, release aldosterone. What is one of the functions of aldosterone? It causes the tubular secretion and excretion of potassium. So if potassium is elevated, aldosterone will get it back down to normal. Goes the other direction. If potassium is low, there'll be less aldosterone being released. Now, ACTH is a hormone that just generally has a trophic effect on the adrenal medulla. It helps maintain the integrity of the adrenal medulla. So if you are missing ACTH, your adrenal medulla will degenerate, and therefore your ability to release aldosterone. So this is, you need some ACTH every day just to maintain the structures of that adrenal cortex. So this is really what's regulating it on minute to minute and daily. But boy, if you have an emergency situation like a hemorrhage, and you really need to start increasing extracellular fluid volume by increasing sodium and water reabsorption, this is the pathway that's turned on strongly. And I've already mentioned that ACE inhibitors play a role there, and I didn't mean to leave all this in here, but it gets to what we've talked about before. ACE inhibitors will inhibit the conversion of angiotensin 1 to angiotensin 2, therefore you lose angiotensin 2 mediated vasoconstriction, you decrease aldosterone release, and therefore decrease sodium and water reabsorption. So ACE inhibitors have an impact on what we were just talking about. Yes?
So if you have high potassium levels, that means you're going to lose more aldosterone?
Yes.
That's how it gets rid of potassium.
Yes. On a minute to minute. As we're sitting here, we have some ADH, we have some aldosterone in our system, okay? And sometimes it goes up a little, sometimes it goes down a little, to keep everything in balance. We tend to think about the extremes, but day to day, we're really more here in the middle. Now, I do want to get to this next. Oh, this is just, I threw this in for the dental students. They have a lot of histology, but here is the adrenal cortex. Here's the adrenal medulla. The adrenal medulla is where you release epinephrine into the bloodstream. The adrenal cortex, it has three layers. The zona glomerulosa, zona fasciculata, zona reticularis, and GFR, glomerular filtration rate. You know GFR. Well, this is how I remember the order. I just go GFR, glomerulosa, fasciculata, reticularis, and then I put these hormones in alphabetical order. What is released from the zona glomerulosa? Aldosterone. What is released from the zona fasciculata? Cortisol, which is important for a lot of things. What's released from zona reticularis? Sex steroids. So that's how I remember it. GFR, and then I put those three adrenal cortex hormones in alphabetical order, and I always have Okay, so the rate limiting step in this pathway right here is the production and release of renin. And renin is found in, here is, trying to remember which, pretty much the same thing. Renin is found in these juxtaglomerulary cells. Most of them are found just outside of the afferent arteriole. There are some associated with the efferent arteriole, but they look very granular, and what they have is they have packets of renin in them. Packets of renin in them. And there are 3 primary releasers of renin from those juxtaglomerulary cells. If the sympathetic nervous system is activated, sympathetic stimulation will cause the release of renin. And then renin converts angiotensinogen to angiotensin 1, and boom, you've got that pathway going on. If blood pressure, you have baroreceptors. Remember, baroreceptors are pressure receptors right here in the afferent arteriole. And if afferent arterial blood pressure drops, like you might have with a hemorrhage, like you would have with a hemorrhage, that drop in afferent arterial blood pressure causes renin to be released. And that sets off that cascade. That causes the release of aldosterone, and what does aldosterone do? It causes your body to conserve sodium in water to help mitigate that fluid loss due to hemorrhage. The other thing is, here in the distal tubule. The distal tubule actually runs right between the afferent arteriole and the efferent arteriole, and there's a collection of cells right here called the macula densa. And what do they have on them? They have a sodium chloride meter. They're constantly measuring how much sodium chloride is going through this area. And if they find that sodium chloride is low, they actually measure chloride much better than sodium. But if they measure chloride and sodium being low, they stimulate the release of renin. So think your way through all these, and all these will kind of make sense, because let's just say, for example, you have a hemorrhage. You have a drop in blood volume. That's going to be decreased venous return, decreased cardiac output, decreased blood pressure. So a decreased blood pressure is going to turn on your sympathetic nervous system. That will cause the release of renin. Decreased aortic blood pressure is going to result in a decreased renal artery blood pressure and a decreased afferent arterial blood pressure. That will cause the release of renin. If you have a very decreased a decrease in extracellular fluid volume, that means less sodium chloride is going to be filtered every minute. So that means there's going to be less sodium chloride being presented to the macula densa. So that's going to cause a release of renin. All those responses cause a release of renin, and that will cause the conversion of angiotensin to tensinogen to angiotensin 1. You go across the pulmonary capillaries, it's angiotensin 2. That will cause vasoconstriction. That also causes the release of aldosterone. And what does aldosterone do? It causes you to reabsorb the sodium in the water you have. So it doesn't get, it tries to prevent it from getting any worse. One thing after another, there's an entire chain of events. Okay, there's another. So I consider aldosterone. Aldosterone is the hormone that if your extracellular fluid volume gets too low, aldosterone and ADH will try to keep it from getting lower and, if possible, raise it. What if you have too much extracellular fluid volume? Well, you have something called atrial natriuretic factor or atrial natriuretic peptide, mean the same thing. Atrial natriuretic factor, atrial natriuretic peptide. This is released actually from several places in the vasculature, but it was first really identified in the atria. And its actions are pretty much opposite of aldosterone. It causes you to lose extracellular fluid volume. Okay? So imagine you have an expanded extracellular fluid volume. Your extracellular fluid volume is too high. That means your venous return will be above normal. That means filling of your atria will be above normal. Your atria are going to stretch. They're going to sense that pressure. And what do? They release this atrial natriuretic factor. They sense increased pressure, they sense increased stretch, they release atrial natriuretic factor. It goes through the bloodstream, it goes to the kidney, and what does it do? Well, it doesn't just go to the kidney. It'll actually cause the release of renin, it'll directly cause the release of aldosterone, and it is also going to increase the excretion at the kidney of sodium and water. So just kind of work your way through that, and you go, well, if extracellular fluid is increased, ANF or AMP is going to function to decrease that extracellular fluid volume closer to normal. So less renin, less aldosterone, less sodium reabsorption, plus it also stimulates the release of sodium. So at any given time, here's your normal extracellular fluid volume. Here's your normal extracellular fluid volume. There's always a dynamic balance between how much aldosterone is in the system and how much ANF is in the system. If your extracellular fluid volume, you just drink a whole bunch of water. If you have an increase in extracellular fluid volume, you're going to have an increase in atrial stretch, an increase in ANF release, and that's going to decrease sodium and water reabsorption in the nephron. If your extracellular fluid volume goes down, that's going to cause the release of renin, that's going to cause the release of aldosterone, and that's going to cause an increased reabsorption of water. So at any given time, in a healthy individual, you have some ANF, you have some aldosterone, but there'll be sometimes you'll have more aldosterone, less ANF. You're going to build your extracellular fluid volume. Sometimes you'll be more ANF, less aldosterone. You're going to be getting rid of your extracellular fluid volume. To homeostatically, this is a homeostatic sensor effector negative feedback loop to help guard your extracellular fluid volume. It's bidirectional control. And I've already talked about this ADH mechanisms and actions. It's dependent on the cyclic AMP signal transduction processes, bringing more aquaporins to the surface. Later on, you're going to hear in other courses about urea. Urea is a molecule that we can put when we are metabolizing amino acids. They have an amine group that can be converted to ammonia, and that is toxic. So we have a process with amino acid metabolism called the urea cycle to take that potentially dangerous amine group and convert it to a very benign product called urea. And that's how we get rid of those amine groups through the urine. Well, it turns out that part of the concentration of the lower interstitial osmotic gradient is because of a cloud of urea. That's all that this slide is here for. That this isn't just due to sodium and chloride and what have you out here, but there is a cloud of urea that helps give some of this increasing concentration gradient to help pull water out when you open up water channels. So you're going to hear about urea and what happens when you have liver failure and you can't make this benign product, and what happens then to the kidney function after liver failure. Okay, so we kind of put some things together. What regulates ADH release? You have two primary mechanisms of regulating ADH release. You have osmoreceptors. They're found up near your hypothalamus. Well, they are in the hypothalamus. And they're constantly looking at the osmolarity of the blood. And if extracellular fluid osmolarity is high, that stimulates ADH release. What does that do? That decreases urine output. Because if you don't decrease urine output, osmolarity is just going to keep getting higher and higher. If extracellular fluid osmolarity is too low, that's going to decrease ADH release, and guess what? You're going to have increased urinary output to get your extracellular fluid osmolarity back closer to normal. You also have left atrial baroreceptors, and they're not just in the left atrium, there are other baroreceptors throughout the body, but bottom line is, if there's an increase in extracellular fluid volume, there's going to be increased atrial distension because of increased venous return. There is a neuron going from your heart, well, there's several neurons, going from the heart up here to the hypothalamus. And ADH is actually released from the posterior pituitary. Its stimulus is, it's stimulated by the hypothalamus, but it's actually released from the posterior pituitary. So that's going to cause a decrease in ADH release and an increase in urinary output. We humans are much better with the osmoregulation than volume regulation. Dogs are much more into the volume than we are, but we have both of these working for us. So, you know, you eat a very, very salty meal, guess what? You will have a decrease in urinary output immediately because you're trying to dilute out your extracellular fluid volume. Now, we've already stepped through this, and I want you to, now that you have some more tools in the toolbox, think about this, hemorrhage and what's going on during the progression and compensation for hemorrhage. And the last section I wanted to get to today is thirst. Thirst is very much associated, very closely associated with the hypothalamus and ADH release. You can have a hyperosmotic thirst, you can have a hypovolemic thirst. It's very, very similar to what happens with ADH. So if your extracellular fluid volume, your extracellular fluid has extra sodium in it, guess what? You get thirsty. And you drink water if it's available, and that will dilute out your extracellular fluid volume. If you sweat a lot and you become hypovolemic, that will also stimulate your thirst center, and hopefully you can then replenish your water supply. 2 people take a drink as soon as I talk about it. And remember, all of these work in the other direction. If you are hypovolemic, the opposite happens. If you're hypoosmotic, the opposite happens. Okay, so we talked a little bit about acid-base. We might next week very, very quickly go through renal compensation for acid-base disorders. But we're going to spend most of next week is looking very closely at diabetes. Okay. Anybody want to meet for questions Sunday, late Sunday afternoon? If you do,